This is a walkthrough of the June 2017 Paper 2 Organic and Physical Chemistry Part 1. Question 1 is about halogenoalkanes. We're starting off with bromopropane, and in reaction 1 we're looking at the nucleophilic substitution with OH minus. So the OH is going to swap places with the bromine. Now it's asked for a displayed formula. Thing to watch out for is making sure you show every single covalent bond, including the one between the oxygen and the hydrogen. You would lose the mark if you didn't show every single bond. Okay, reaction 2, again nucleophilic substitution, is reaction with ammonia. So first of all, it's asking you what type of mechanism it is. So nucleophilic substitution, and the condition, if we want to ensure that the primary amine is the major product, then we need to make sure that we use an excess of ammonia. If we don't, we'll end up with secondary amines or even tertiary amines. Okay, and then 1.3 is asking us to calculate a mass produced. So first step, I would always write out the balanced equation, okay, so that you can work out what the MR of the various things involved are for working out the yield. So there we go, we've got the MRs of the bromopropane and the aminopropane. And then if you work out how many moles you've got at the start, so we do the mass divided by the MR. And then we can work out how many moles of the amine we would expect to produce. So that's going to be the moles times the percentage yield. And we can work out how many moles we would expect to produce. So 75% of 0.205. And then if we convert that into grams, we need to times the moles by the MR of the amine. It says to give your answer to an appropriate number of significant figures. Everything in the question is given to 3 sig fig. Remember, top tip, if you write that at the end, it makes it much easier to remember. When we turn over the page, we're still talking about these reactions of the halogenoalkanes. We can see we're asked for what happens if we carry out reaction 2 under different conditions. And this time we're going to make C9H21N. So we can see we've got 3 times as many carbons. So we can see that we're going to make the tertiary amine rather than the primary amine. So draw a skeletal formula for this. You're going to have the nitrogen in the centre and then 3 propyl groups. This is also checking that you can draw a skeletal formula, so making sure that you count that you've got 3 carbons in each of those chains. And the functional group classification here is a tertiary amine. The next part of the question is about reaction 3, which would be elimination from the halogenoalkane. We use hydroxide ions again, but this time in ethanolic conditions to force it to do elimination. And in the elimination, a hydrogen and the bromine are removed to form a double bond. This is the other kind of reaction that can happen with halogenoalkanes. So to draw the mechanism, first step, draw out your starting material, making clear all the different bonds, particularly the ones that are important. And then we can show how the OH here, rather than acting as a nucleophile, is actually acting as a base. So rather than swapping and attacking the carbon that's on the bromine, it attacks a hydrogen and takes it away, breaking the bond between the carbon and the hydrogen, forming a double bond, and then releasing the bromide ion, hence forming an alkene. Overall, this is a nice question summarising the different reactions of halogenoalkanes, that you can do nucleophilic substitution reactions or you can do elimination reactions. Question 2 is a nice question about rate equations and rates of reaction, and first step is just checking that you know how to draw a tangent. So really important here that your tangent is in place and goes through the origin because it's at t equals 0. It's always a good idea to continue your tangent through the axes so that you can get as big a triangle underneath to work out your gradient. So when working out the gradient, we're going to look at the change in the concentration of A, divided by the time taken. So you can read both of those off of the axes to get a calculation of 0.5 over 11.5, which comes out at 0.043. Mark scheme's quite generous on this one and allows a little bit of leeway on exactly the gradient that you choose for that tangent. So 2.3 is over the page is fairly straightforward. I've copied out the rate equation just for reference from the previous page. So if we know that the initial rate is now 1.7 times greater, then we know that the change to the concentration of A must be equivalent to the square root of 1.7 because the rate is proportional to A squared. Therefore, we know the change, if I just type that into the calculator, the square root of 1.7 is... So that's 1.30. And then if we know that the concentration of A at the start was 0.5, which we read off the graph on the previous page, then the new concentration is going to be 0.5 times 1.3. And again, just tap that into your calculator. So 0.65. Question 3 is again on rates, but with this time they've given you a rate equation and some information and asked you to work out a rate constant at this temperature and give the unit. So if you rearrange the equation for the rate equation to give you K, it would be rate over the concentration of C and the concentration of D. And then it's just a case of plugging in the different numbers from the question. So 3.1 times 10 to the minus 3 divided by the concentration of C and the concentration of D will give us an answer. Okay, so that's 2.8 times 10 to the minus 2. And then we just need to work out the units for the rate constant. So we're going to write out the units for rate are moles per decimetre cubed per second, and then we know we're dividing that then by moles per decimetre cubed, and again moles per decimetre cubed. That's the concentration of C and the concentration of D. Cancel out things that appear on the top and the bottom, and then you're left with, so we've got seconds to the minus 1 on the top and moles dm to the minus 3 on the bottom. So the moles on the bottom becomes moles to the minus 1, dm to the 3, seconds to the minus 1. The second part of this question relates to the Arrhenius equation and how the rate changes with temperature, but rather than expecting you to draw an Arrhenius plot, you just need to rearrange the Arrhenius equation and then plug the numbers in. So you're being asked to work out the activation energy. So if we rearrange the equation, we'll find that the activation energy is equal to R times T times ln of A minus ln of K. So we know that ln of K from the information we're given. We know what K is, so we can work out that ln of K is going to be natural log of 2.8 times 10 to the minus 2. So in my calculator, that's minus 3.58. We know T is given as 25 degrees C, so we need to convert that into Kelvin. So if we add 273, that's 298. So we can then write everything out. So we've got R is 8.31 times 298 times, and then ln of A is given to us in the question. So it's 16.9 minus minus, so therefore plus 3.58. So, and if we evaluate that, tap it and pop everything in, we're going to end up with an answer of 50,716 joules per mole. Now the question has asked for an answer in kilojoules per mole, so to go from joules to kilojoules we just need to divide by 1,000 and end up with an answer of 50.7 kilojoules per mole, which I believe in the mark scheme you're allowed to round up to 51 kilojoules per mole. It doesn't state in the question to give it to any particular number of significant figures, so a little bit of leeway given on that. So question 4 is about the nucleophilic addition of potassium cyanide to pentanal to form a hydroxynitrile. The first question is for naming the hydroxynitrile that's produced. Remember, when you add a nitrile, when you add CN and react with cyanide, you end up with a longer chain. So we've got 6 carbons, so it's hexane nitrile, and it's got a hydroxy on the second carbon. So it's 2-hydroxyhexane nitrile. How would you distinguish between the 2 separate samples of the stereoisomers? So remember, enantiomers are optically active. They rotate the plane of polarised light in opposite directions. So you could test and check in a polarimeter what the plane of polarised light was, and the 2 enantiomers would opposite directions, which is all you need to put for the 2 marks. So 4.3 says explain why the reaction produces a racemic mixture. You don't need to draw a diagram to get the marks for this, but I have drawn a diagram just to make it easier to explain. So if we remember that the aldehyde, the carbonyl group on the aldehyde, or indeed on a ketone, is flat, it's planar, which it means it is able to be attacked by nucleophiles equally from above and below. So the nitrile, or the cyanide group, the CN nucleophile, can attack equally well from above and below. And this means that you're going to end up with an equal amount of both enantiomers. So if we show this nucleophile attacking, so the CN, the cyanide group can attack equally well from above the plane or from below the plane, from either side, which leads to you getting a racemic mixture, so of both enantiomers, both stereoisomers, in equal amounts. You must mention the equal amounts because it wouldn't be a racemic mixture if it didn't have equal amounts of both. Incidentally, a racemic mixture would not rotate the plane of polarised light because the 2 enantiomers would cancel out. So question 4.4 asks about an isomer that, when it reacts with potassium cyanide, doesn't show the stereoisomerism. So we're going to be looking for a product that doesn't have 4 different groups on the central carbon, so therefore doesn't have a chiral carbon. So if we suggest that the isomer that we start off with has the carbonyl group on the central carbon, then when it is attacked by the cyanide, you end up with the hydroxy group and the nitrile group both on the middle carbon, but because you've got an ethyl group on either side, it no longer has 4 different groups around the carbon and no longer has a chiral carbon atom. Question 5 is about esterification and also about equilibrium. So as you can see, we've got a carboxylic acid and a diol. So when they react together, we're going to get a diester. So I would start by drawing the diol first, or the diol part of it first, and show it's going to form an ester where the 2 alcohol groups are. with two carboxylic acid groups. So our structural formula, it doesn't state exactly what type of structural formula you need, so you can get away with that. Okay, the next part is asking you about what happens in the equilibrium. So we need to remember from the start that we've got 2 moles of ethanoic acid and we get 2 moles of water at the end, and take this into account when working out the equilibrium amounts. So it tells us what we've got at the start. I'm just going to put a little 2 in front of the ethanoic acid and in front of the water to remind me that I'm twice the number of moles are reacting. So it's like doing an ice table, but you haven't got time, space in the middle to do the change part. So in the working out underneath, I know that if I work out how much the ethanoic acid has changed by doing the 0.47 take away 0.18, then I know that that's 0.29. So I know the water is going to have changed by that amount, so it will have gone up by 0.29. And I know that the amount of diester produced is going to be half of that. So I need to do the 0.29 in half is going to be 0.145. And then the diol will have gone down by that amount because it's only changed by 1 molar amount. So 0.205 take away 0.145 will give us the amount that the diol has gone down by and what it is at the point of equilibrium. Five point three asks for an expression for the equilibrium constant. So if we remember, Kc is going to be the concentration of the products divided by the concentration of the reactants. Now at this point you could just write the ester at the top and the water at the top, and write the carboxylic acid and the alcohol at the bottom. Remember, because there's 2 moles of water produced, then it's the water goes on the top squared. You could write ester, you could write the formula. You're not expected to draw the whole structure. So Kc, so products on the top, reactants on the bottom, remembering to square anything that is 2 moles of in the equation. Then it says justify why the total volume doesn't need to be measured. Well, if you work out, we've got 3 moles on the top of the equation and 3 moles on the bottom of the equation. So because there's the same number of moles in the products as there are in the reactants, then any volume would cancel out. We would have volume 3 times on the top and volume 3 times on the bottom. So the volume would cancel. So it doesn't matter that we don't know what the total volume is. So 5.4, they've been nice to you here. They've given you some data rather than you using, just in case you couldn't work out the equilibrium data from before, and they're asking you to use that data to work out, well, they've given you the equilibrium constant and they want you to rearrange it to work out what the equilibrium value of the ethanoic acid is. So if we quickly jot down that expression for the equilibrium again, this time I've cheated and put ester and water and acid rather than writing out the molecular formulae. And then if we rearrange it so that we get the acid, so we want to put the acid at the start. So if I put acid squared, and then Kc is going to move to its place on the bottom. Okay, now if we substitute all the numbers in, if all the numbers are substituted in, we can get a value. It says give your answer to an appropriate number of significant figures. So we get a value of 0.623, but we now need to square root it to get the concentration of the acid. So, and everything needs to be given to 3 significant figures because all of the values you were given to work from were to 3 significant figures. Question 6 is about amino acids. Remember, the data booklet has the amino acids you would need. You're not expected to remember them. So just for reference, I've drawn phenylalanine from the data booklet first for you, just to remind you what happens when it forms as zwitterion. So phenylalanine looks like this. And when it forms as zwitterion, if you remember, the carboxyl group loses the hydrogen, so acts as an acid and donates its proton, and the amine group becomes protonated. So you end up with phenylalanine with a negative charge on the carboxyl group and an NH3 plus on the amine group. Okay, the next one asks you to draw serine at a high pH. So let's draw the structure of serine first of all. So again, it's going to have a carboxylic acid group and an amine group. And then the R group, in this case, from the data book, is CH2OH. So if we put this at a high pH, then what's going to happen? It's going to act as an acid, so it will lose its proton. Okay, now it says draw the structures of both dipeptides when the two react together. So the first way round would be phenylalanine and then serine, so with an amide link between. So if we draw phenylalanine first, and then remember that when it forms an amide, the carboxylic acid group becomes, so we get C double bond O N, and then you're going to get serine. Okay, so this is our first dipeptide. And the second dipeptide would be serine and then phenylalanine. So if we draw serine first, and then remember we've got our amide link. So draw the basic dipeptide structure, and then go back and add the R groups in the correct order. So first of all, the CH2OH for serine, and then the CH2 benzene ring for phenylalanine. So there you can see you end up with 2 slightly different structures because of the different way that the 2 amino acids can join together to form the dipeptides. So the final part of this question asks about the amide link that's formed in the acylation reaction between an acyl chloride and the primary amine. This would be a nucleophilic addition-elimination reaction. So it's like nucleophilic addition, but then it goes on and does elimination afterwards. So a slightly more complex mechanism. So if we start off by drawing the acyl chloride, and if you remember, the carbon of that carbon-R-carbon is going to be very electropositive because it's got a chlorine and an oxygen on it. So then the amine, so the lone pair on the ethylamine, so the amine lone pair is able to act as a nucleophile and attack at that carbon. And the electrons in the double bond move up to the oxygen to form a negative charge. So we'll draw an intermediate. So we've got a negatively charged oxygen, the chlorine's still there, the ethyl group's still there, and then we've got the amine attached. And then in the next step, so our amine's got a positive charge. In the next step, the lone pair on the oxygen moves back down to reform the double bond of the carbonyl, and the chloride ion gets released. So, and another part of that, so to remove that positive charge from the amine, you don't actually need to draw a full amine coming in and taking it away. You just need to show that the bond on the hydrogen breaks and the electrons move on to the nitrogen. Okay, so I'll just draw the final product. You don't need to for the mark scheme. The mark scheme is all about showing the curly arrows, showing the movement of the electrons, but the final product would be the amide. There you go. It asked for the IUPAC name of the organic product. So first of all, we count how many carbons there are in the amide, and then count how many are on the N. So it's going to be N-ethyl, because there's an ethyl group attached to the N. And then the amide part has 3 carbons, so it's propanamide. So N-ethyl propanamide. So question 7 is checking that you can identify different functional groups, and really important that you use the minimum number of tests. So we can see K and M have both got carboxylic acids, K has got an OH, N has got an aldehyde. So let's think about the logical sequence. Now, I'd write this out like a method. So step 1, step 2, step 3. So step 1, if you test all of the 4 samples to divide them up into those that are carboxylic acids and those that aren't. So if you use something like sodium carbonate or sodium hydrogen carbonate and look for effervescence or the production of carbon dioxide, then you can check and say that you've got K and M as one half of the group, and L and N must be the other two because they don't have the carboxylic acid group. So I'd write that out. So test all 4 samples with sodium carbonate. It's important you describe what you'd observe each time. So the carboxylic acids will effervesce. So identifying K and M would both effervesce or give off carbon dioxide. L and N would not. So once you've split them into 2 groups, K and M, L and N, you then need to describe the test you would do to distinguish between K and M, and then another test that you would do to distinguish between L and N. So if I look at K and M, K has a hydroxy, an alcohol group, and M does not. So we'd need to do a second test where we identify the one with the alcohol group. So the way I've done that, I've said if we warm K and M with acidified potassium dichromate, K is going to turn the solution from orange to green. Remember, you've got to describe what you'd observe. M would not react. So, and then for 3, I've said because if we use Tollens reagent, and we could use Failing solution instead, but Tollens reagent and a warm water bath, N will produce a silver mirror, L will not react. So although it's a 6-mark level of response question, if you write it out like a method, and the really important thing is putting in a logical sequence so that you use the minimum number of tests and giving what you would observe for a positive test or for each of the different compounds. So question 8 is about nitrobenzenes. First, 8.1 is asking you to write the equation for the reaction of conc nitric with conc sulfuric to form the species that reacts. So we've got to make that nitro group that acts as an electrophile. So we've got to somehow turn HNO3 into the NO2+, which is the group that does the attacking of the benzene ring. So I think this is an equation just to remember really. So the sulfuric acid and the nitric acid, we get NO2 plus H3O plus 2 lots of HSO4 minus. Okay, so the name of that mechanism then, all of the reactions that attack the benzene ring are electrophilic substitution. So where we swap hydrogens on the benzene ring for different electrophiles. They all have the same mechanism. So what we're going to do, start off by drawing the benzene ring. And it's, well, we've got a nitro already on it. So we've got nitrobenzene. And what happens is we're going to attack that with another nitro group, so this NO2+, and we draw a curly arrow from the benzene ring to the NO2+, and show our intermediate, which shows the ring with its existing NO2, and then where the NO2+ is attacked, it needs to have an NO2 and a H. And this distorts the ring, so we end up with a horseshoe shape, and that horseshoe shape needs to centre around where we've got the NO2 attacked, and there'll be a positive charge. We then show an arrow from breaking the bond between the hydrogen and showing the electrons moving back into the ring. Okay, and then show the resulting 1,3-dinitrobenzene. So the rest of question 8 is about thin layer chromatography, which you've obviously covered as a required practical. So it says we do it in a fume cupboard. We've got the 2 different dinitrobenzenes and how they respond differently to the TLC plate. It says there's a pencil line drawn. So the first question asks you to deduce the RF value. Now, actually looking at the values they've given you to choose from, you could probably work out which one the answer is. But just in case they don't do that, I will show you how you do it. So you measure the distance to the spot, you measure the distance from the start line to the solvent front. Obviously, you will have got different distances because you've printed this out, and I'm doing this on my iPad screen. But I've got one of them's 4.6 centimetres, one's 7.4 centimetres. If you divide the distance the spot moves to the distance the solvent front moves, and it came out as 0.62. As I said, you can probably tell by looking at them, D is the only one that's an answer that's significantly more than halfway, which if you look at the spots, that one would be your answer without actually doing any measurements. So you then are asked to state in general terms what determines the distance travelled by a spot in TLC. So you can talk about the difference in whether it's soluble or whether it has a retention to the solid, or you can talk about different affinities. Both are acceptable ways. So it's a balance between how soluble the substance is in the mobile phase, which is the solvent, compared to how much affinity it has, or how much retention it has to the solid stationary phase, so the plate. And it really is a balance between the two. So if something's more soluble, it's going to move further. If something is more stuck to the solid, to the solid plate, the stationary phase, then it will not move very far. So this next question says, give another practical requirement when placing the plate in the beaker. It's really important that the depth of the solvent is quite low and doesn't go above the line where you've put your start dot. So the pencil start line is really important. Okay, so it then says that we do a second TLC experiment and we use an identical plate, same solvent, okay, but the RF value was found to be greater than that of 1,2-dinitrobenzene. So deduce the relative polarity. So we know what they told us at the start of the question is that the plate is polar and the solvent is non-polar. Okay, so the relative polarity. So if something's got a greater RF value, it must be more attracted to or have a greater affinity to the solvent than to the plate. So it therefore must be more non-polar, okay, or less polar. So the relative polarities, the 1,4-dinitrobenzene is less polar than the 1,2-dinitrobenzene, hence having a greater RF value. And it's all to do with whether it's more attracted to the plate or attracted to the solvent. So the greater RF value means it's more soluble, or has a greater affinity to the solvent. So in this final question, they say we're doing 1,2-dinitrobenzene again, but we use an identical plate, but this time we've added ethyl ethanoate to the solvent mix. Now, ethyl ethanoate is more polar. So it says, is the student correct or not when they say that the RF value is going to be greater? Well, the student would be correct, so it's important that you state that, because the addition of ethyl ethanoate is going to make the solvent, or the mobile phase, much more polar. Okay, which means that, so the 1,2-dinitrobenzene so our mobile phase is more polar, so the 1,2-dinitrobenzene will be more soluble in this solvent. And therefore it's going to move further and have a greater RF value. Question 9 is about DNA, and again you're expected to use the data booklet to help you answer the questions. I'm going to put some little bits from the data booklet on the page just to remind us. So if we remember when we're looking at the DNA, so the deoxyribose, it attaches to the phosphate in the 3 and the 5 position, and it attaches to the base in the 1 position. And if we start off at the oxygen at the top of the pentagon and count round. Okay, so this is the bit that everybody found difficult when we did it in class. It's where you're having to draw on the hydrogen bonds. So I've put thymine and copied it across from the data book. If you remember, where I've coloured in red there and highlighted is where it attaches to the DNA, that back to the rest of the strand. The hydrogen bonds are going to be where I've highlighted in yellow. So on the molecule of adenine, I would draw on where the hydrogen bonds are going to be. Okay, remember, so there's a lone pair on the N is going to hydrogen bond to a hydrogen on the thymine. And one of the hydrogens on the NH2 is going to hydrogen bond to a lone pair on the oxygen on the thymine. So if I draw those in position first, and then try and draw the thymine molecule in around where those oxygen and nitrogens would be, remembering from looking at the data book where it hydrogen bonds. So this is quite tricky, but if you need to sort of rotate it in your head or on the page. Okay, and there you go. So 10 is about lots of different isomers of C6H10O2. First one is this IUPAC name, so I would count the longest chain. So we've got 1, 2, 3, 4, 5 with the carboxylic acid in, so it's going to be based on pentanoic acid, but it's got a double bond on the second carbon, so it's pent-2-N-oic acid, and it's got a methyl group on that second carbon, so 2-methyl pent-2-N-oic acid. And then because the two heavier groups are on the same side, we need to give it a Z. So Z2-methyl pent-2-enoic acid. Okay, the next question, they've given you the gas constant and told you a temperature and a pressure. So that's your clue that you're going to need to use PV equals nRT. So the first thing it says, write an equation. So write out the C6H10O2 plus oxygen to work out how many oxygens it reacts with and how many carbon dioxides are going to be produced. Okay, so the volume of CO2 produced, so if we know that the total volume of gas was 335, but then after it's been reacted and the carbon dioxide has been removed, it's decreased to 155, we can work out the volume of CO2 produced is going to be the 335 minus the 155, which is 180. And if we then rearrange PV equals nRT to give us N, which is number of moles, and we say we've got PV over RT, then, and remember that the pressure needs to be in Pascal, so 105 is going to become 105,000. The volume needs to be in meters cubed, so 180 centimeters cubed needs times in by 10 to the minus 6 to get it into meters cubed. And then we're going to divide that by R, which is 8.31, and the temperature needs to be in Kelvin, so 25 plus 273 is 298. So from that, N comes out as 0.00763. Okay, so that's our moles of CO2. So moles of P must be that divided by 6, because the moles of CO2 over 6 would give us the moles of P that we had at the start. So 0.00127. And then we need that as a mass, so we need to say the MR of P, so 6 lots of 12 plus 10 plus 2 lots of 16. So that MR is 114. So 0.00127 times 114 will give us a mass in grams. So 0.145 grams. So the answer needs to be in milligrams. So to get from 0.145 grams into milligrams, we need to times it by 1,000. So the answer is going to be 145 milligrams. So in 10.3, you're being asked to piece together information from the IR and the NMR and put them together to work out what the structure is. So if we look at the IR first of all, I've already circled the fairly clear, there's the OH group, and that would be the OH in a carboxylic acid if you look at the data sheet. And then around 1700, we've got the C double bond O peak. If you then move on to the carbon NMR, you can see that there are 4 carbon environments. And as there's 6 carbons in total in C6H10O2, we know that there must be some sort of symmetry. So I'll just do a little sketch at the side here so we can see we know there's a carboxylic acid group from the IR, And then we know that there's 4 different carbon environments. So if I sketch this cyclic compound, because it tells you in the question it's cyclic, then we can see that it would have, those 2 carbons would be identical, those 2 carbons would be identical, and then there's an extra one there and there. So we would have 4 different carbon environments. So if we put that all together into a written answer, this is what we would do. So structure of Q drawn more neatly. So we've got a cyclic 5-membered ring, so 5 carbons in a ring in a pentagon shape. And then the carboxylic acid group on there. So that is C6, O2, and check it's got the right number of hydrogens, but it has. Okay, so evidence from figure 4, you can say there's the OH peak in the acids at, and then quote the numbers that it says on the data sheet, so 2,500 to 3,000 centimetres to the -1. And that is sufficient for your evidence from figure 4. And then evidence from figure 5, there are 4 peaks showing 4 carbon environments. And this is the only cyclic structure you can come up with that has a carboxylic acid group and 4 different carbon environments. Also from figure 5, you can say that one of the peaks is quite high up. It's at 160 to 185 parts per million, and this would be due to it being a C double bond O. In an acid, and this is more information you can get from the data sheet. Continuing with carbon 13, question 10.4 is asking you how you would tell the difference between R and S. I've copied the bit from the data sheet to the side here so you can see. So we can see that they would both have the carbons that have got the carbonyls on would be at 190 to 220. Okay, but if you then look, R has then got 4 carbons that would be at 20 to 50. Okay, so there would be 4. So 4 of those carbons are in a next to a C double bond O. If you look at S, it's got 2 of those carbons that are next to a C double bond O that would be at 20 to 50. But the 2 CH3 groups are further away, they're next to a CH2, so they would have a peak at around 5 to 40. Okay, so they're just on the ethyl group. So use the data sheet and, really go through and go, where would these be? So we can write out our justification for that. In terms of how many peaks you'd have in total, both R and S are symmetrical. So because they're symmetrical, they would both have the same number of peaks, and they would, although there's 6 carbons, the symmetry down the middle of the molecule means that you would only see 3 peaks for each of them. So in this next question, we're looking at proton NMR spectra for the same compounds R and S. So I've cut and pasted R and S below so that I can refer to them while going through the question. It says in the question to justify the statement using splitting patterns. So it's really important. We're not so interested in looking at the data book, but thinking about what the splitting patterns would be. So if we look at R first, the 2 CH3 groups, the proton environment of the CH3s, so they're equivalent, and the 2 CH2s are equivalent. So we're going to get 2 peaks because it's symmetrical in a ratio of 6 to 4 or 3 to 2. And if we think about what those peaks are going to be, they have no neighbours. So the CH3 is not next to the CH2. The CH2s are equivalent, so they don't cause splitting. Therefore, you're going to get two singlets for R. If you look at S, you've got the CH3s again, which are equivalent, but this time they're next to the CH2s, and the two CH2s are equivalent. So we're again going to get two peaks because of the symmetry, but the CH2, because it's next to the CH3, is going to be split into a quartet, and the CH3, because it's next to the CH2, is going to be split into a triplet. If you remember, the splitting rules are that they split into n plus 1, neighbour plus 1. So writing that up then, so R will have two singlets. Okay, if you wanted to get into it, you'd say they would be in a ratio of 3 to 2. S will have a quartet and a triplet, or a triplet and a quartet. The difference being the carbonyl in R stops and gets in between the CH3 and the CH2, so you can't see, so they can't be neighbours, they can't do any splitting. Number of peaks, because of the symmetry, both molecules will have two peaks. So 10.6 is about 5-hydroxyhexanoic acid. So if you draw this out, you'll see that it's got 6 carbons, and it's got a carboxylic acid at one end, and at the other end, or not quite at the end, but one away from the end, it's got a hydroxy group, so an alcohol. And because it's got a carboxylic acid and an alcohol, this means that it's able to, where you've got an alcohol and a carboxylic acid, you can form an ester. So it can either, as it say, wrap around itself because it's long enough and form a cyclic ester, or it can, if you get multiple molecules in a row, they can form a polymer, a polyester. So the structure of the cyclic compound would be, what do we get if we turn the whole thing round into a ring with an ester link? So so you can see the ring we've drawn there. And then the repeating unit of the polyester would be drawing the whole thing out, but removing an OH from one side and an H from the other, because what happens when it would polymerise is water would be removed. And we call this type of polymerisation condensation because you're removing water. So this next question is about a different polymer formed by this monomer U. And when you look at the structure of U, you can see it's got a double bond, which is your big clue that it's going to do addition polymerization rather than condensation polymerization. So that double bond is going to open out. So when drawing the repeating unit, I'd always start with where the double bond is and draw it opened out, and then draw the other groups around where that main double bond would be. It's important when drawing repeating units that you draw extended bonds on either side to show where the polymer would extend, so it would continue. So by drawing the extra lines at either side, it shows it would continue this way. Okay, and it says justify why this would be not biodegradable despite having an ester structure in it. So because this polymer chain is held together by strong covalent bonds between the CCs, they're non-polar, there's no point of attack, and therefore the polymer chain cannot be attacked by hydrolysis or by nucleophile attack or anything. Whereas the ester links, they can be hydrolyzed, but that wouldn't actually infect the integrity of the polymer chain. So E, F and G are all weak bases, and in this question you're being asked to explain the difference in the base strength and give the order of increasing base strength. So if you look at them, so E, the nitrogen, and bearing in mind that the whole thing that affects them being a base is that the lone pair on the nitrogen is able to accept protons. So in E, the nitrogen is directly attached to the benzene ring. In F, it's on the end of an alkyl chain that just happens to be on the end of a benzene ring. And in G, it's in between a benzene ring and an alkyl chain. So you need to remember what we learnt in class about the effect of the benzene ring on the availability of that lone pair, and also the effect of alkyl chains. So base strength is determined by how available the lone pair is, because the nitrogen has to be able to accept protons. When it's on a benzene ring, the lone pair gets kind of brought into the delocalized structure of the electrons that are in the ring, the delocalized ring structure, and it makes it less available to accept a proton. So we would expect, of these three, we would expect E to be by far the weakest of the bases, because its lone pair is not very available. Now, alkyl groups actually push electrons towards the nitrogen and have an inducing effect. So the more alkyl groups there are on an amine, so a tertiary amine would be a stronger base than a secondary amine, and a secondary amine would be a stronger base than a primary amine. So the more alkyl groups there are, the more of an inducing effect they have, and the more they push and make available that lone pair so that it's able to accept protons. So if we look, so we would expect F to have by far the strongest base strength, because it's got its nitrogen is on the end of an alkyl chain, and that alkyl chain is going to be pushing those electrons onto the nitrogen. G, on the other hand, is kind of in between the two, so it's going to have an inducing effect from the alkyl chain, but the lone pair are going to get also drawn into the delocalized ring structure. So I would expect G to be a base strength in between E and F. This final question is particularly challenging and probably the trickiest one on the whole paper, as it's asking you to come up with an organic synthetic route for producing amine F from methylbenzene. So as always with these organic synthesis, I would draw the structure of where you're starting and what you're finishing with and see what you can kind of deduce. So if we start off with methylbenzene, I've drawn at the side here, and then look at what the structure of F is from the previous page. So it's a benzene ring with CH2, CH2, NH2. So what do we know? We know that we're trying to grow the chain here. So we're going from CH3 to CH2, CH2. So we need to add an extra carbon. And to do that, we know we're going to need to use a nitrile group. So adding cyanide as a nucleophile is the only way that you can grow the alkyl chain. But to begin with, we've got to find a way of attacking the CH3 on here. So at the moment, we've got a methyl group, and we know that they're not very reactive. And the only thing you can really get a methyl group to react with would be to use free radical substitution and something like chlorine or bromine. So my first step for this, I would use chlorine and UV light and do free radical substitution and make a halogenoalkane, because once I've got a halogenoalkane, there's a point of attack and something that we can then do a nucleophilic substitution on. So our next step then would be to take this halogenoalkane, the chloro, so the benzene ring with the CH2Cl, and we're going to need to do a nucleophilic substitution and use cyanide so that we get a nitrile group on there to grow the length of that chain. So the reagents and conditions for this you do need to remember. So we would take and react it with potassium cyanide. The potassium cyanide needs to be aqueous, so because it's a salt, it needs to be dissolved in water, but then that needs to predominantly be in an ethanol solvent to prevent, if you were to just use water, you would end up with an OH doing nucleophilic substitution instead of the CN. So that's why the ethanol's in there. That nitrile then needs to be reduced, okay, to make it into the amine. So reduction takes place, and the method you need to remember for this particular specification, how we do that reduction, is you would react it with hydrogen, and you need some kind of metal catalyst, and the catalyst you could have used, the one that is in the textbook is nickel, but you could use palladium or platinum. But hydrogen gas in the presence of a metal catalyst, for example, nickel. You could also use lithium aluminium hydride. It's not specifically mentioned in our specification, but it is mentioned in the mark scheme as an alternative answer. Okay, so that quite a tough question, but 5 marks. I wouldn't worry about trying to write lots. You can get the marks just from drawing out the different steps in the synthesis. And that's the end of this paper.